In this video then we're going to look at the sine, cosine and tangent ratios, and this follows on from a previous video where we looked at the ratios of special triangles. Now the special triangles that we looked at, I can just draw on this sheet of paper here. So I'm going to draw well, what is this? An equilateral triangle and a square. So some of the most basic shapes in geometry, and they're very useful to sketch initially or to have in mind so that we understand how the sine, cosine and tangent ratios work. Now the reason we're looking at this is because the sine, cosine and tangent ratios are the standard way of finding unknown lengths, sides, if you know an angle and a length, and I'll show you how that works. But they're so useful, and they've been used for so many centuries because it's the most effective, most efficient way of answering those kinds of problems. So we've got an equilateral triangle, but what I've done is tipped it over to one side, if you like. So it's slightly at an angle here. This, in other words, is the vertical, and the sine refers to this triangle, this term sine, because sine comes from the Latin sinus, which comes from an earlier word which means bowstring. And you can imagine this as, I suppose, the string of an arrow. If I draw on the bow, you'll see what I mean. So here's the bow going here, and it's just a kind of arc here, I suppose. Let's just draw it a little bit neater like that. So there's our bow. Then here's the string, and we're going to actually bisect this. Okay. This construction. So here's the arrow. So where the arrow cuts this line here, gives us our opposite angle. Opposite side rather to this angle here, and we're going to be looking here at the opposite and this, if you like, our bowstring, the hypotenuse. So the opposite divided by the hypotenuse gives us our first ratio. The sine ratio is the opposite over the hypotenuse. Okay, well, let's go back to our equilateral triangle and now return us to where we were in the previous video, where we'd identified the special nature of half of an equilateral triangle, which is a 60, 30, 90, 60, 30, 90 degree right angle triangle. Okay? So in a 60, 30, 90 or 30, 60, 90 triangle, we discovered that there's a fixed ratio of sides, and that's very easy to remember. The shortest side is, or we just define as 1, and the ratio of the shortest side over the hypotenuse gives us our first fixed value for the sine function, 1 over 2, opposite over hypotenuse. So we say the sine, and in fact what we can do is just shorten this still further. So let's just write it SIN, which is the normal convention. Although in some countries I think they do write SINE. But sine of 30 degrees simply means the opposite side, whatever that length is, divided by the hypotenuse. Now, of course, in most triangles, it won't neatly be 1 over 2, so it won't just be a half. But once you've divided the, if this was 10, for example, and this was 20, then you'd have 10 divided by 20, but 10 divided by 20 simplifies to just a half. Okay? So sine of 30 degrees equals 1 over 2 equals a half. And for any size triangle, as long as it's a 30, 60, 90 triangle, that will be true. So sine of 30 is a constant. It's always a half. And a half is, of course, if we want the decimal version of a half, is exactly 0.5. So sine of 30 is always 0.5, and most people can remember that and use that frequently. Now what about the sine then of 60? Well, the sine of 60 degrees is also going to be the opposite over the hypotenuse, because that's what sine means. So where's the opposite now? Well, the opposite side is no longer this side. The opposite side to 60 is this one. And we've seen that the ratio of the three sides is always 1 to 2 to root 3. So by Pythagoras, we have the third side here, the sort of middle-sized side as root 3. Therefore, the sine of 60 must be the opposite, root 3, divided by the hypotenuse, which is 2. And root 3, we can say, is roughly 1.7, I think it's roughly 1.73, and in this case we're going to have to keep these things quite accurate. Now, what I'm going to do is just erase that equal sign, because although with sine 30 a half does equal 0.5, here we're approximating this surd. So whenever we've got a surd and we convert it to a decimal, we must write approximately equal to. Okay, so it's approximately equal to 1.73, but not exactly. So that's the exact form, and this is only an approximate value. Okay, but we'll get it as close as we can, or as close as we need to for the problem. So divided by 2, what do we get? Well, for this calculation, let's go to one side here. We've got 2 divided into 1.73. Now we're going to put a 0 point, carry that 1. 2 into 17, or 17 divided by 2 then, is going to give us 8. With, because 2 8s are 16, with 1 remainder, so there's the 1 there. 13 divided by 2 is going to give us, well, 12 divided by 2 is 6, so we're going to write down 6, and again carry 1. And 2 into 10, or 10 divided by 2, gives us 5. So it's not an exact value, it's exact here, but it's not an exact value. Nevertheless, it should be pretty close to the answer for what is sine of 60 degrees, 0.865. And of course you can verify this on a calculator, or you can look up, as people used to, a table of all the sine values and find sine 60 and see if it is that value. But it's something like that, and we could write ... approximately equal to. Okay, if the sine of 30 degrees is a half, or 0.5, and the sine of 60 degrees is, and I'll give the exact value only here, root 3 over 2, what about the cosine? Now the cosine means the complementary ratio, the complementary sine. But of course we want to shorten all of that. So for convenience, instead of saying complementary sine, we say co, and we just write S-I-N-E, or to shorten it even further, just cos. So usually we would just write cos. So the cos of 30 degrees is the complementary angle. And to get the complementary angle, what we do is we take our 30 degree here, and instead of finding the opposite over the hypotenuse, still over the hypotenuse, but now we're going to look at this ratio, the adjacent side over the hypotenuse. Okay, so we can tell that this is opposite. If we draw an arrow, you'll be able to see that very clearly. That's the opposite angle. So the adjacent is the one that isn't the hypotenuse, which is always the same, never changes. It's the one it's the other leg, if you like, the other side, which in this case is going to be root 3. So we write root 3 divided by the hypotenuse, which is 2. Now you'll notice here that the cos of 30 degrees is the same as the sine of 30 degrees. In fact, they're equal. So now we can see why we're using this idea of the complementary sign. The cosine is complementary to the sine. Okay, there's a kind of, if you like, there's a close relationship. But it's not just a relationship, it's a complementary relationship. So we say is approximately equal to 0.865 again. Okay? And we don't need these dots actually, let's just erase these dots. Okay, so sine 60 equals cos 30. What about cos 60? What do you think? Well, let's work it out and see if you're right. So the cos of 60 isn't going to be the opposite of the hypotenuse, it's going to be the adjacent side over the hypotenuse. In other words, 1 over 2. And 1 over 2 doesn't approximately equal, it equals 0.5. Therefore, we've got another match here. The sine of 30 degrees equals the cosine of 60 degrees. Sine of 30 degrees equals the cosine of 60 degrees, just as the sine of 60 degrees equals the cosine of 30. And this is really useful because it's, if we're going to remember some of this, it's going to give us less to remember. Okay? Now, let's move over to our square here. Now, it's a square at the moment, but just like the equilateral triangle, I'm going to halve it, bisect it, to give us a 45, there we go, a 45, 90 degree triangle, right angled triangle. And again, this is a very special triangle. We saw in the previous video that if we set one of the sides at 1, the other side obviously will be 1 as well. And by Pythagoras, we work out that the hypotenuse has to be the square root of 2, or just root 2. So that's the ratio of sides. It's a 1, 1, root 2 triangle. And the sine values here, well, the sine of, let me give myself a little bit more room here. The sine of 45 degrees, the sine of 45 degrees is going to be what? Well, again, remember these values can go up and down, but they stay in the same proportion. The ratio stays the same. So the sine is the opposite. Let's just choose this one. The opposite side, which is over there. The opposite over the hypotenuse. The hypotenuse is always the sine. It's always opposite the right angle, the 90-degree angle, in fact. So you can always spot the hypotenuse, immediately identify it as the side that's opposite the right angle. But here we're talking about the opposite over the hypotenuse, so sine 45 equals 1 over root 2. Now usually we won't see it written like this. The convention is always to have your surds in the numerator at the top of the fraction, not at the bottom, and it's very easy to get rid of it, so we just convert this. And we convert it by rationalizing the denominator, which means multiplying by root 2 over root 2, which doesn't change the fraction, it just changes the way it's arranged. So what we've got now is 1 times root 2, which is root 2, divided by root 2 times root 2, in other words root 2 squared, which is just 2. Okay, so in the 45, 45, 90 degree triangle, the sine of 45 then is root 2 over 2, and we can convert that to decimal. It's going to be approximately equal to 1.4, it's something like 1.41, I think, divided by 2. And let's just leave off the 1 because we're only going to get an approximate value. So we've got, let's do it over here, 2 into 1.4 is 2 into 14, 0.7. Okay? So approximately equal to 0.7. But again, bear in mind that the sine of 45 is better better to use the exact form, which is root 2 over 2. Okay, what about the cosine of 45 degrees? The complementary sign. Well, strangely enough, and in this special case only, the cosine of 45 must equal the sine of 45. Let me just write that a little bit clearer. So if I write the cosine of 45, then I'm going to say that equals, okay, let's just use a green pen here, they exactly equate. Now, why is that? Well, if we think of, again, this angle here, the opposite is 1, the adjacent is also 1. Okay, so the adjacent side down here is also 1. And if it's the adjacent over the hypotenuse, it's always over the hypotenuse with both the sine and the cosine, then it must be exactly the same. In other words, what we've got is the adjacent, which is 1, divided by root 2, which is rewritten root 2 divided by 2, root 2 over 2, approximately equal to 0.7. But that's only an approximate value. Okay, now, finally, we've got the third function. So we have the sine, the cosine, and the tan now. So the tangent is a little different from the sine and the cosine. It's not exactly complementary, but it fits into, if you like, a nice triangular relationship, I suppose you could say. Now, how do we remember all these things? Very, very straightforward. We remember it by the sine is the opposite side length over the hypotenuse. Okay, and I'm just using the division symbol like that. Now it reads as SOH, and people usually think of that as so they remember it as SOH or so. Now the cosine, let's use a different color. The cosine is adjacent over hypotenuse, so phonetically, if you like, the way we say it is so ka. So we remember the sine is the opposite over the hypotenuse, opposite divided by the hypotenuse. It's the ratio of opposite over hypotenuse, and the cosine is the adjacent over the hypotenuse. So it's that ratio of A over H, A divided by H. Finally then, well, what other combination have we got here? We could change this round and then we get 3 other trigonometric ratios, but just for most purposes all we need is the sine, the cosine, and this third ratio, which is the tangent. And the tangent then is the opposite over the adjacent. So now we've got so, S O over H, ka, C, A over H, and toa, tan, is O over A. And that's how most of us remember it. The sine is opposite over the hypotenuse, the cosine is adjacent over the hypotenuse, but the tangent is the opposite over the adjacent. Why is it called the tangent? Well, originally it would have been measured in a slightly different way, with a tangent that would be coming up against a circle. There was a ratio there which it turned out using similar triangles was equivalent to the opposite over the adjacent, exactly equal. So that's how it came to be called the tangent. But the tangent is basically the opposite side over the adjacent. So if we go back to our 30, 60, 90 triangle, where's our tangent of 30 degrees? So in this case, with a 30-degree angle, our tangent is going to be the opposite, TOA, opposite, which is 1, okay, divided by, let's just adjust that a little bit. So tan of 30 degrees is 1 divided by the adjacent, so not the hypotenuse, okay, the adjacent can easily be identified as the side adjacent to the angle, if you like, but basically it's the other one. If you can find the opposite, then the adjacent is the other leg that isn't the hypotenuse, okay? So pretty easy to do, and it's 1 over root 3, okay? And once again, we're not going to leave it like that. We're going to multiply by root 3 over root 3, giving us root 3 over root 3 squared, which is 3. So the tan of 30 degrees is root 3 over 3, which is approximately equal to, well, if we think of root 3 as about 1.7, I think it's about 1.73 divided by 3 then. So we're not working in exact forms here, but I'm going to work this out to give us a fairly accurate decimal version of the tan of 30. How do we do this? 1.73. We probably need another 0, won't we? So 3 into 1, 0. 3 into 17. Well, 3 into 17 goes 5. So that's 3 times 5 equals 15. Carry 2. Now we've got 23 divided by 3. Well, that's going to be 7. We have 2 left over, and it's going to be about 7 again, isn't it? I'm going to say it's approximately equal to 0.58, okay? Because we're going to have 6 here, but that will round up anyway. So 0.58. So 1.73 divided by 3 gives us 0.58. There we go. To 2 decimal places, and you can check on your calculator again if that is indeed accurate. Whatever that is, though, remember it's dangerous to use these decimals because it's much better to use the surd form, because we know that tan 30 is exactly root 3 over 3. And again, for any triangle that will be true as long as it's a 30, 60, 90 triangle. So tan of 30, tangent of 30 is always, for well, it's a constant value, so it's always root 3 over 3. So what's the tan of 60 degrees? Well, if you think of this, the other angle here, and you think of the adjacent and the opposite just swapping round, but the hypotenuse always staying the same. The hypotenuse never changes, okay, when we swap angles here. This is always the hypotenuse. Let's just, okay. So we just swap these numbers around. In other words, we've got the adjacent, which is going to be here. The adjacent side is 1, so it equals 1. Okay. The adjacent side over the, what am I doing? The opposite, TOA, T-O-A. I have to remind myself. It's the opposite, which is root 3 over 1. In other words, it's the inverse of the tan of 30. Let's just rewrite that then. Or if you like, the reciprocal. So we have root 3, which is the opposite, divided by 1. Okay? And root 3 divided by 1 is simply root 3. And root 3 as we've said, is approximately equal to 1.73. Okay? Now, what about the 45, 45, 90 degree triangle? So the tan of 45 degrees now, well, that's got to be the adjacent, the opposite over the adjacent, which is 1 over 1. 1 over 1 is simply 1. So the tan of 45 degrees is 1 over 1 equals 1. And of course, there's nothing else for us to do. Now we have all of our values, our ratios for the trigonometric ratios for these two types of special triangle. We have the sine of 30 degrees, which is a half, equal to the cos of 60 degrees, which is also a half. We have the sine of 60, which is equal to cos 30, both of them equal root 3 over 2. We have the tan of 30, which is root 3 over 3, and the tan of 60, which is just root 3, so they're not equal to one another. Over here we have the sine of 45, which is root 2 over 2, and easy to remember, the cos of 45 is also root 2 over 2. The tangent, though, of 45 degrees is 1 over 1, which is simply 1. Okay. Now finally, just to illustrate some of these ideas and work out a few more interesting patterns, if we think of the sine function, another good way of remembering it, apart from this idea of the bowstring, I think the bowstring is quite good, but if we think of just pulling this hypotenuse then nice and taut, so if we bring in a hand we can see that's being pulled there, stretched up to the edge of this circle here, then the opposite is the line that hangs down. In other words, it's being stretched by gravity. I think that's a good way of thinking about it. As we move it round the circle here, it's a radius then that's being stretched taut. If you think of it as a chord, think of it as a piece of string, I suppose. Then there's another piece of string hanging down from these pinched fingers here, and that's the opposite. So the opposite over the hypotenuse. Good way to think about the sine, and to remember that as the primary trigonometric ratio. All right, if that's the sine, what about this tangent? Now I said earlier on that it was to do with constructing a tangent against this circle, but let's just show you how that works. So if I do draw a tangent, which is going to be perpendicular to the radius here, okay, so it just touches the circle at this point, and there's a 90-degree angle here. Well, what has the tan function, which is the opposite over the adjacent, so the green one here over the orange here, what has that ratio got to do with this line that I've just drawn, the tangent? Well, to see that, what we have to do is just mirror this triangle and stretch it a little to create a similar triangle. So if we think of this as the first triangle, let me show you the second triangle that I'm going to draw. Okay, and just stretched up. Now the angle is the same, but what's happened is the hypotenuse now is at the bottom. It's going along the horizontal axis here. And the opposite and the adjacent are now here and here. Okay, because the right angle, let's draw it in. Okay, let's just draw the right angle up here. Because the right angle is here. So don't forget that triangles will appear in any way up that you like, and in exam papers they certainly won't necessarily be orientated the way you might want them. You have to get used to seeing them in different ways. Well, on this occasion we've drawn it so that the tangent, the opposite over the adjacent, is indeed drawn as a segment of this line that we call the tangent in geometry. So that explains why we call it the tangent ratio. Okay, now finally we have this formula here, and this explains something that you may well have already noticed by working through the calculations that we worked through earlier, that the tangent isn't a separate thing. It's very closely, it's intimately related, if you might say, to the sine and the cosine, and this is the relationship. The tangent of any value, let's say 30 degrees, the tangent of 30 degrees would equal the sine of 30 degrees divided by the cosine of 30 degrees. And equally, if that's true, you would say that the sine, so therefore the sine of any angle, let's call it theta, the sine of theta has got to equal the tan of theta, okay, times, we just do a dot, times the cosine of theta, cos theta. So just by rearranging there, in other words, what we've done is we've multiplied both sides by cos. If we want to think of, well, what's the cos of theta then, in terms of the other two trigonometric ratios, the cos of theta, well, if we rearrange again, in other words, by dividing this through by tan, then the cos of theta has got to equal the sine theta divided by tan theta. So as long as you remember tan theta equals sine over cos theta, you can also find out what sine theta and cos theta is. And these are really useful ways of substituting in alternative values. You might have the sine and the tan but not the cosine, and that's how you get the cosine very, very simply. But with this, the tan equaling the sine divided by the cosine, is that true in the first place? Well, let's have a look at the values we had before. So we had sine of 30 degrees, we saw equals a half. Very easy to remember. The cosine of 30 degrees, well, the cosine of 30 degrees, again, fairly easy to remember, is root 3 over 2. And if the sine of 30 degrees equals a half and the cosine of 30 degrees equals root 3 over 2, we can simply test whether the tangent is the sine over the cosine by taking these values, so half divided by root 3 over 2. Well, if we divide by root 3 over 2, we must be multiplying by 2 over root 3, like that. And now we multiply across to get 1 times 2 is 2, 2 times root 3 gives us 2 root 3. These will cancel, so divide top and bottom by 2, and you get 1 over root 3, which is indeed, as we saw, the value of tangent. Let's try the same thing then with 45 degrees. So does it work for all angles? Let's use a different colour. Okay, so the sine of 45 degrees this time. Well, the sine of 45 degrees is 1 over root 2, and we saw that that's usually written root 2 over 2. And the cosine of 45 degrees is also root 2 over 2. Okay, so if we calculate the sine of 45 degrees divided by the cosine of 45 degrees, what have we got? We've got root 2 over root 2, over 2, root 2 over 2, divided by root 2 over 2 is the same as times 2 over root 2. Equals, well, 2 root 2 in the numerator and 2 root 2 in the denominator. Both cancel to get 1 over 1 equals 1. And the tangent of 45 degrees is indeed 1. Let's do one more, final one. So this time we've got the sine of 60 degrees. Well, the sine of 60 degrees is root 3 over 2. cosine of 60 degrees is 1/2. And root 3 over 2 divided by 1/2 is the same as root 3 over 2 times 2, or 2 over 1, let's say, equals 2 root 3 divided by 2. The 2's cancel, so divide top and bottom by 2 gives us root 3 over 1, in other words, just root 3. And 1 over root 3 is the tangent of 30 degrees, 1 is the tangent of 45 degrees, and root 3 is indeed the tangent of 60 degrees.